So we've already talked about how substances that have more intermolecular forces will have a lower vapor pressure because they have a higher boiling point. So if you make a solution, it also affects things. Whether you've got a lot of intermolecular forces or a little, it'll affect things. But they definitely do mess around with those intermolecular forces. So we've got 2 containers of water right here. And so if you, like, just imagine this is like maybe 85. You know how like a container of water, you can kind of see it boiling a little bit. But you can also like see it'll condense on the side and fall back down. So the vapor pressure's enough, maybe not quite yet to pull off that stopper, but it's definitely pushing on it. Like if you loosen that stopper with it being 85, it would probably come off right away. So that's how something that has pure water in it does. And remember the water, remember he had those intermolecular forces, had the hydrogen bonding, holding it together. So water, for something this size of water in that molar mass, it has an incredibly high boiling point, or something that size. Because you take just oxygen, that's 32, and so that has a higher molar mass than the water, which is 18. And yet oxygen is a gas at room temperature, but water isn't. So it's got that, and it's got the polarity. So it takes a while to get it enough energy in there to get it boiling. So if you look over here though, these purple pieces represent like some kind of a solute being dissolved in the water. And you'll notice that the it's like the solutes kind of block the way, in a way, of the water. Also, the solutes can have interactions with the water in many cases, especially if you're a strong electrolyte. That sodium, we've still got the hydrogen bonding going on, but then on top of it, the sodium's like, oh, I like that side of the water, and then chlorines might be like, I like that side of the water. So they're holding it in and adding more molecular forces. So solutes can also do that. So they're kind of getting in the way of the water being able to get out. They can, like, he's really hemmed in here. He's going to have to travel all the way around to get out. Plus, they are creating more intermolecular forces to deal with. So that's why at 85, pure water, will be kind of like condensing and boiling. You definitely see the vapor, but you won't see it as well if it has the solute in there at 85 Celsius. Now, over here at the problem, vapor pressure lowering, we have this equation right here. So I just want to point out that this should not look like a new equation either. Back in Gen Chem 1, there was a full chapter on gases. And in Gen Chem 1, if you had a mixture of gases, your total pressure was equal to, or your total pressure times the mole fraction of one of the gases was equal to the pressure of one of the gases. So if you had like 2 gases, you'd figure out the mole fraction of one of the gases times the total pressure, and then it's the partial pressure. So this should look really, really similar. This number right here, so this is the vapor pressure. So this is a constant that you would get from a chart, or it'd be given in the problem. So this problem, it's given in it. It isn't labeled, but it's given. And you just need to multiply it times the mole fraction, which you've seen and worked with. And that'll give you the new vapor pressure of the solution. You should always expect the new vapor pressure to be lower because vapor pressure lowers when you make a solution. So if we read this, the pressure of pure ethanol is this. So this is the number we get from the chart right here. And the charts will have different temperatures on them. So you got to make sure you've got the temperature from the that matches the problem. So the pressure of pure ethanol, so that's this value right here. That's the pressure. And then it says 10 grams are added to 10 grams of ethanol. What is the vapor pressure of the solution? So we've got our molar masses right here. And let's go ahead and do the rest of it. So we've got to convert this into our mole fraction. Then we just multiply it times that number. So it's not too hard. So I'm going to say 10.0 grams of that one times the 46.02 grams in 1 mole. And I'm going to go ahead and write the other one out too. 100 grams. Do you know what? That is actually 100 grams, the ethanol. 100 grams of ethanol. And then this one is 10.0 grams in 1 mole. And the molar mass is 92.09. So 100 divided by 46.02 gives me 2.12. I'm keeping extra sig figs here, 97. 10 divide by 92.09. 0.10859. That smells at that one. So remember, we have to do the vapor pressure of the solution. This is the thing that is the solute. If you read the question, the ethanol, that's the solvent. So it's the pressure that solvent's going to have the pressure it generates as it moves across. So I just need to say 0.10859 over parentheses 0.10859 plus 2.17297. That's the mole fraction times, and then my 0.178 ATMs. Remember, no, mole fraction comes out unitless. We just put that in the calculator. 2.172968 plus 0. Go back here. 0.10859 parentheses times 0.178. All right, so that gives us that the pressure is equal to 0.008471. Now, our sig figs here is we've got 1, 2, 3 sig figs, and did these conversions over here. They had at least 3 sig figs in them. So we're going to do 3 sig figs, and this is ATMs. So notice it's not like a huge pressure, but it's significant enough for us to do calculations with it. Maybe you can imagine this not on a tiny scale in a beaker, but maybe in a plant that's using osmosis to move, I don't know, like solutes around or solvents around, not solvents. That pressure, times maybe 1,000 grams instead of 10 grams, which is not really that much. That's something.